So, dear students, welcome back to another lecture on structural analysis. We are dealing with plastic analysis. In this lecture, we will be talking about plastic analysis of continuous beams. So, as you can see on we are having a continuous beam which is having three spans. So, span AB, BC, and CD, and each of the spans are having variable plastic moment capacities. So, AB is having a capacity of 2 MB, BC is having a capacity of 1.5 MB, and CD is having a capacity of MP. Now, the question is we need to find out the plastic moment capacity required for each of the sections. So, the question is to find the plastic moment capacity required for each span. So for each span AB, BC and CD, what is the plastic moment capacity required? Now the first thing we have to understand is the collapse is going to occur whenever we are considering the collapse of the continuous beam. The collapse is going to occur as a single span. Okay, so at a time any one of the spans will only be failing, so we are only going to consider separate beam mechanisms. Okay, so we will be considering a beam mechanism for AB, we will be considering a mechanism for BC, and similarly we will be considering a mechanism for CD. So that will be the way in which the continuous beam failure will be assessed. So first thing we have to do is, let us consider the span AB. So if we consider the span AB, we have to look for the number of possible plastic hinges. The number of possible plastic hinges is one fixed support is there, so that is a possible plastic hinge. Interior support is also a possible plastic hinge, and there will be a span point in the middle of the span where the bending moment will be maximum. So in total there are three possible positions of plastic hinges. And what will be the indeterminacy of the span? The indeterminacy of the span will be 2, because interior support you can consider it as a fixed support. So this beam can be considered as a fixed beam, and the plastic hinge will be the degree of indeterminacy will be 2. So the number of plastic hinges required to form a mechanism will be 2, degree of static indeterminacy plus 1, that will be 3, and the number of mechanisms that are possible will be n minus ns, that is 3 minus 2 equal to 1. So for span AB we require a minimum of 3 plastic hinges to form, so as to form the mechanism. So let us see the mechanism for AB. So this is A, this is B. So at the fixed support one plastic hinge will be formed. At the interior support also there will be one plastic hinge that will be formed, and since it is symmetric, the loading is symmetric, at the middle of the span also there will be one plastic hinge formed. So this will be the assumed mechanism, and if this angle is theta, then this distance will be 4 theta. This angle also will be theta since it is symmetric. These two angles will also be theta since it is symmetric. Now AB is having a capacity of 2 MB. The hinge, at the middle is also having a capacity of 2 MB, whereas the hinge at B is the intersection of two sections, one having a capacity 2 MB and another having a capacity 1.5 MB. Therefore, the hinge at B will only be having the capacity 1.5 MB because it is the intersection point. Okay, so the intersection point, the lower capacity will be critical, or that will limit the capacity of the plastic hinge. So we will choose the lower value 1.5 MB. So now this is the geometry of the mechanism for the span AB. So having found out the geometry of the mechanism, now what we have to do is we need to write the virtual work equation. So external virtual work is equal to the internal virtual work. So if we calculate the external virtual work, the total load, it is a UDL, therefore it is total load into average displacement. Total load is 40 multiplied by 8. This is the total load. The average displacement is half into 0 plus 4 theta. So this is the average displacement. So this is the total external virtual work. This is equal to virtual work done in the plastic inches, that is 2 mp into theta plus 2 mp into theta plus theta plus 1.5 mp into theta. So this if we do the calculations, we are going to get here as 640 mp is equal to 7.5 mb theta. So if we calculate, we will get mb as 85.33 kilonewton meter. So this is the value of mb considering the collapse mechanism for the span AB. Now let us consider the collapse mechanism for the span BC. Now if we consider second is span BC. So we are going to consider span BC again as both ends fixed, because both the interior supports can be considered as fixed ends. Interior supports can be considered as fixed ends because they are having partial fixity and therefore can be considered as fixed ends for the sake of analysis. So if we consider BC, we are having two loads here. One is a 100 kilonewton load, and we also have another load that is 150 kilonewton. Now again, the number of plastic hinge locations are, number of possible plastic hinges are, at both the supports there can be plastic hinges, and under each concentrated load there can be plastic hinge, therefore it is 4. Static indeterminacy is 2. Number of plastic hinges required to form a mechanism will be 2 plus 1, that is 3, and the number of possible mechanism will be n minus ns, that is 2. That means we have to consider two mechanisms here. So let us consider mechanism number 1. So mechanism number 1 is, let us say a plastic hinge is forming at B, another plastic hinge forming at C, and then a plastic hinge forming under the load 100 kilonewton. So this is our first mechanism. So if this angle is theta, this will be 2 theta, then this would be 2 theta divided by 4. So that will be theta divided by 2, and this would be theta, that is theta by 2 into 2. So it will be theta. Also we need to write the capacity. So this point is intersection of two sections, one having 2 MB capacity and one having 1.5 MB capacity. So we have to choose the lower capacity, so 1.5 MB. Here also it is 1.5 MB, and point C is the intersection of two sections, one having capacity 1.5 MB and another having a capacity MP. So we have to choose the lower value, that is MP. Now the geometry of the section is complete. Now we have to write the virtual work equation. So if we write the virtual work equation, internal virtual work is equal to external virtual work. So the internal virtual work will be 1.5 MP into theta plus 1.5 MP into theta plus 0.5 theta plus theta by 2 into MP. This is equal to 100 into 2 theta plus 150 into theta. So if we try to simplify this, what we are going to get is 4.25 mp theta is equal to 350 theta. That is, mp is equal to 82.35 kilonewton meter. So as per mechanism 1 for the span BC, we are going to get this as the value of MP required. Now we have to go for mechanism number 2 for the span BC. So mechanism 2 for BC. So for mechanism 2 for BC, here we will consider the plastic hinge being formed below the 150 kilonewton load. So if this angle is theta, this distance would be 2 theta, and this angle becomes 2 theta divided by 4, that is theta by 2, and this distance becomes theta by 2 multiplied by 2, that is theta. Now having got all the angles, this angle will be theta and this will be 0.5 theta. Similarly, the capacity of the plastic hinge here will be 1.5 mp, this will be 1.5 mp, and here it is intersection of two sections, one 1.5 mp and another one is mp. Therefore we have to choose the lower value, that is mp. And here we have 150 kilonewton load and here we have 100 kilonewton load. So writing the virtual work equation, that is internal virtual work is equal to external virtual work. So the internal virtual work is 1.5 mp multiplied by theta plus 1.5 mp multiplied by theta plus 0.5 theta plus mp into theta. This is equal to 100 multiplied by theta plus 150 multiplied by 2 theta. So if we try to solve this, simplify this, what we are going to get is 4 mp theta is equal to 400 theta, that is mp is equal to 100. So from mechanism number 2 for the span BC, we are getting a value for mp required as 100 kilonewton meter. Now let us try span CD. So again, span CD, when we see the interior support can be considered as a fixed support, whereas the exterior support has to be considered as it is. So exterior support has to be considered the way it is. Now the load that is acting is 80 kilonewton and the distances are 2 meter and 4 meter. So again, the number of possible hinge locations are, one is the fixed support or the interior support, that is 1. Second one is under the load, that becomes another one. So it is total 2. Degree of static indeterminacy of a propped cantilever is 1. Number of possible plastic hinges to form a mechanism is 2. And the number of possible mechanism is n minus ns, that is 1. So the mechanism will be, one hinge will be formed here, another hinge will be formed under the load, and thus forms the mechanism. So if this angle is theta, then this becomes 2 theta, and if this is 2 theta, then this becomes theta divided by 2. So this angle is theta and this angle is 0.5 theta. And this particular point C is the junction of 1.5 mp and mp. Therefore we have to choose mp here, and here also it is mp. So this concludes the geometry of the mechanism for the span CD. Now once the geometry is complete, we can apply the virtual work equation, that is internal virtual work is equal to external virtual work. So mp into theta plus MP into theta plus zero point 0.5 theta is equal to 80 into 2 theta. So this is the virtual work equation. If we try to simplify, we are going to get 2.5 MP theta is equal to 160 theta. That is, MP is equal to 64 kilonewton meter. So finally, if we try to summarize the results that we got from the various mechanisms. So first one is mechanism for span AB. So these are the mechanisms considered, and this is the MB required. So from the span AB, when we the mechanism for span AB, we got it as 85.33. From the first mechanism for span BC, we got the value as 82.35. From the second mechanism for span BC, we got it as 100. And for the mechanism for span CD, we got the value as 64 kilonewton meter. So all these are in kilonewton meter. Now off here we have to choose the largest required value, because if we provide only if this is the largest value that is required, largest MB requirement is this one, and therefore the section that we are providing should be capable of resisting the largest moment requirement, or the moment demand. So we will be choosing the largest MB value. Okay, because if we are designing only for 64, then it is not capable of taking 100. But if we are capable designing it for 100, it is capable of taking all the lower values, so we will be choosing it as 100. So if MP is chosen as 100, then the plastic moment capacity required for span AB, span AB it is 2 MB, that is 200 kilonewton meter. For span BC, it is 1.5 MB, that is 150 kilonewton meter. And for span CD, it is MP, therefore it is 100 kilonewton meter. So this is the answer that is required. So basically what we are trying to do is we are trying to find out the plastic moment capacity that is required to resist the loads safely. And how do we find them out? We consider the mechanism for each of the beam sections, and when considering the mechanisms, the interior supports can be assumed as fixed supports, okay, because they are having partial fixity, and we simply have to analyze individual beams for their plastic moment capacity. So after having got all the plastic moment capacities, we will be designing the structure for the largest capacity requirement, so that it is safe for all other cases. I hope this is clear to you. Now what we will be doing is, let us consider one more problem related to this. Now in this question we are having a two span continuous beam ABC, and in the span AB we are having a load 40 kilonewton, and in span BC we are having a load 20 kilonewton per meter, and the span is 6 meter and it is 2 MB. Now again, to solve this problem, what we have to do is we have to consider mechanism for each of the individual spans. So if you are considering span AB, so the interior support can be considered as a fixed support. So this becomes a propped cantilever. So n is equal to 1 in number of possible hinge locations. One is at the fixed support, second one is under the load, so it is 2. Degree of static indeterminacy is 1. Number of plastic hinges required to form a mechanism is ns plus 1, that is 2. Number of mechanism is n minus ns, that is 1. So a plastic hinge will be formed in this fashion. So this will be the plastic hinge. So if this angle is theta, it is going to be symmetric. So this will be 2 theta and this will be theta since it is symmetric. And we have the load 40 kilonewton. So this angle will be theta and this will also be theta. And this is MP. B is the junction of two values, that is MP and 2MB. We have to choose the lower value. So the geometry of the mechanism is completed. So once the geometry of the mechanism is completed, we can apply the virtual work equation. That is MP into theta plus MP into theta is equal to 40 into 2 theta. So 3 MP theta is equal to 80 theta, that is MP is equal to 26.67 kilonewton meter. So this is the first value of MP required that we have got. Now next is we have to consider the mechanism for span BC. Again, the interior support can be considered as a fixed support and the exterior support has to be considered as it is, and we have a UDL on it. So the magnitude of the UDL is 20 kilonewton per meter and the span is 6 meter. So again, as you know, to form there is only one mechanism, and to form that mechanism, two plastic hinges have to be formed, one on the fixed support and the second one, as you know, for a propped cantilever, the maximum span moment occurs at 0.414 from the propped end. So this distance is 0.414 L. So that is 0.414 into 6. We will be getting it as roughly 2.5 meter. So 2.5 equals 0.414 into L, that is 0.414 into 6. So we'll be getting it as 2.5 meter. So if this is 2.5 meter, this will be 3.5 meter. So if this angle becomes theta, then this height is 2.5 theta and this angle becomes 0.72 theta. So the geometry has to be completed. Also, this particular point B is the intersection of two moment capacities. One is MP and the other one is 2MP. So this becomes 2MP, MP, the lower value, and this becomes 2MP. And the load that is acting is a UDL 20 kilonewton per meter. Now what we have to do is we have to apply the geometry is completed, so we can apply the virtual work equation. That is, internal virtual work is equal to external virtual work. So the internal virtual work is MP into 0.72 theta plus 2MP into theta plus 0.72 theta. This is equal to the work done. The work done is 6 into 20, that is the total load multiplied by the average displacement. So if we try to there is So here if you look, there is a slight mistake here. That is the loading that is given here is not 20, that is rather it is 30 kilonewton per meter. So this will be 6 into 30. So if we simplify this, what we are going to get is, this is going to be 4.16 mp theta. This is equal to 225 theta. So if we solve, we are going to get mp equals 54.08 kilonewton meter. So again, if we try to summarize the results, what we can see is, from mechanism number 1, that is the mechanism for AB, we have got a value of MP required as 26.66, and from mechanism for BC we got the value as 54.08 kilonewton meter. So what we have to do is, always we have to design for the larger capacity, so that all the value lower than that will be safe. So therefore, choosing MP as 54.08, so the plastic moment capacity that is required for AB is, AB the requirement was MP itself, that is 54.08 kilonewton meter, and for BC it was 2 MP, so it is going to be 108.16 kilonewton meter. So this is how we do the problem. Sometimes it may also be asked to find out the section modulus that is required. Okay, so the plastic section modulus that is required may be asked to find out. In such cases, we know that MP is equal to Fi multiplied by ZP. So what we can do is, we can calculate ZP as MP divided by Fy. So Fy is 250. So in that way, this corresponding section modulus that is required can also be calculated. So what we have done in this session is, we have tried to calculate the plastic moment capacity of continuous beams. And the idea of solving plastic moment capacity of continuous beams is, we are going to consider each span, and for each span we are going to calculate the plastic moment capacity required. And if a particular span is having multiple mechanisms possible, then we have to explore all the possible mechanisms. And after having considered all the mechanisms for each span of the continuous beam, then we have to compare and take the largest value of MP required and design each span for that the corresponding values of plastic moment capacity required. So with this we conclude our discussion on plastic moment analysis for continuous beams, and in the next session we will be discussing about plastic moment capacity or plastic analysis for portal frames. Thank you.